Hey guys, this video is just going to be on sampling distributions of means, and that's for section 9.3 in the book. These are just practice problems. I would suggest looking through the notes if you want to read all the vocabulary that's in this section. So the Dasani Bottling Company uses a filling machine to fill plastic bottles with water. The bottles are supposed to contain 300 milliliters. In fact, the contents vary according to normal distribution with a mean of 298 milliliters, standard deviation of 3 milliliters. What is the probability that an individual bottle contains less than 295 milliliters? So all we have to do for this problem is z-score, where z-score is x minus the mean over standard deviation, and x here is going to be 295. So 295 milliliters minus the mean, which is 298, over my standard deviation, just like a normal z-score problem. And we end up getting -1 when we do that z-score. If I look up -1 in my z-table, remember I always want you guys to write out your picture, your normal curve. So -1's right here. I'm going to shade to the left because it says less than. So I shade left. And then when I look up this into the sheet, I get 0.1587, I think. Now I want you guys to always write, there's two things that you keep forgetting to do. I need you to draw a picture. I need you to draw this. And I need you to write in a sentence. So I'm going to be better about doing that myself. So what does this mean? This means that the probability that one bottle, they said an individual bottle, so one bottle contains less than 295 milliliters is 15.87%. So if you think about that, let's say the bottles on the Dasani bottles, they say 298 milliliters on the label. Well, 15.8% of the time sometimes is less than what it says on the bottle. Now, looking at the same problem, now they want what is the probability that the mean contents of the bottles in a 6-pack is less than 295 milliliters. Well, if you look at the bottom of your reference sheet, on the second or third page, it says for a sampling distribution, the mean of x bar is going to be whatever the mean is. So here the mean is 298. But the standard deviation changes. The standard deviation for any samples that are more than 1 is going to be the standard deviation over the square root of n. So here we have standard deviation is 3 over my size n. N is, they said, a 6-pack, so 6 bottles. And the standard deviation I get for that is 1.2247. So now I can do z-score with this new mean, which it was the same, and this new standard deviation. So I have 295 minus 298 over my new standard deviation, which is 1.2247. And that gives me a z-score of, and I'm going to draw my curve for this. Now it says -2.45. I'm going to say that's about here. Do I shade to the right or to the left? Well, they said less than 295. Remember, 298 would be right here for the middle, the mean, and then 3 standard deviations down from that. And so I'm going to shade to the left because it says less than. And I'm going to take whatever that is in the sheet, in the z-score sheet. When I look that up, I get this to be 0.0071. So, the probability that the mean contents of a 6-pack of bottles, of water bottles, is less than 295 milliliters is 0.71%, very small. Now think about it. For one bottle, the probability of one bottle being less than this amount, less than 295, was about 16%, which is a higher probability than having 6 bottles. Does that make sense? Yeah. If I had one bottle, if I was to choose one bottle, it's more likely that I pull out one bottle that has less than 295 milliliters. But if I had 6 packs, and I pulled out a whole bunch of 6-packs and found the means of those, it's not as likely to pull out a percentage, bottles, the mean bottles of 295 milliliters. It's less likely to happen because I have more bottles. An insurance company sees that in an entire population of homeowners, the mean loss from a fire is $250 with a standard deviation of $300. The distribution of losses is strongly skewed right. Could you find the probability that a single home has a loss over $260? Well, the only thing we know how to do to find probability is use z-score. Can we use z-score for this? No, it says it's strongly right skewed. When do we use z-score? We use z-score when it's a normal distribution. So can I do this problem? No. The distribution is skewed right. All right, if the company sells 10,000 policies, what is the probability that the average loss will be greater than $260? Well, can I do the problem now? Yes. If you remember when we did the cupcake lab, CLT, because this is a large sample, due to CLT, I can now do the problem. What happens when I increase my sample size, especially when the sample size is bigger than 10 or 15, we can now do the problem because, as you saw in our lab, the more samples we had, the more normal the distribution became. So, because due to CLT, we can do the problem. The bigger the sample size, the more normal the distribution becomes. So now I'm going to find the mean. The mean, remember, always stays the same, so it's still going to be 250. What does change is the standard deviation. Standard deviation was 300 over the square root of n. Square root of n here is 10,000. 10,000 policies. So if I calculate that out, I get my standard deviation to be 3. So let's do the z-score now. So I'm trying to see if it's greater than 260. So 260 is my x minus my mean, 250, over the standard deviation, which we just found right here, is 3. So I have 10 over 3, which gives me 3.33. Now let's draw our normal curve. And 3.33 is a little area. It's very small towards the end of the graph. If I look it up in the chart, I get the left side to be, because remember, whenever you're looking something up, it tells you the left, 9996. Do I want the shaded left side? No, I want the right. So what do I have to do? I have to do 1 minus that, 0.9996. And that gives me 0.0004. So if I were to write this in a sentence, the probability, if the company sells 10,000 policies, the average loss from a fire would be, that it's greater than $260 would be 0.04%. Is my final answer. David's iPod has 10,000 songs. The distribution of playtimes for these songs is heavily skewed to the right, with a mean of 225 seconds, standard deviation of 60 seconds. Suppose we choose an SRS of 10 songs from this population and calculate the mean playtime of these songs. What are the mean and standard deviation of the sampling distribution? So that's just simply knowing what the mean and standard deviation for sampling distributions are. Well, I told you that mean was same thing. It's just mu. Standard deviation is standard deviation over the square root of n. So the only thing I need to pick out is whatever my n is, my standard deviation, and my mean. So look for those three numbers. I have this is my mean, 225 seconds. Standard deviation is 60 seconds. And n, what is n? Is it 10,000? No, because David's iPod has about 10,000 songs. So that's his population. And my SRS is 10 songs. So the simple random sample, my sample size, which is whatever n is 10. So the mean for this is going to be 225 seconds. My standard deviation is 60 over the square root of 10. So when I calculate that, I get 18.97. 37, if you want to continue, seconds. Remember, the mean of a sampling distribution is the mean of the population. And remember that the standard deviation is standard deviation over the square root of n. Because now I have 10 songs that I have to consider into my standard deviation. The standard deviation decreases. Remember that from our lab, that if the standard deviation originally was at 60, remember that your spread ended up shrinking down when your sample size increased. So it decreases here. It's now 18.9737. Using the same problem, how many songs would we need to sample? So we're looking for n, which is very unusual. We're looking for our sample size. If you wanted the standard deviation of the sampling distribution, it would be 30 seconds. Well, our formula for standard deviation is standard deviation over the square root of n. So I have this. I want standard deviation of my sampling distribution for x bar to be 30. I also know from the last slide that 60 was my standard deviation, and I'm looking for the square root of n. If you could think back to algebra, when you solve for this, I could flip this and switch these two, because technically 30 is over 1. So I'm going to have the square root of n be equal to 60 over 30. Or you can multiply both sides by square root of n and then divide by 30, which gives you the same thing if you want to do it that way. 60 divided by 30 is 2. So I need to get n by itself. How do I get rid of that square root sign? I square it. Yes, we still have to remember all of our algebra skills. N is equal to 4. So how many songs would I need? I would need 4 songs if I wanted my standard deviation to be 30. And then here are just some multiple choice questions that I thought looked cool from one of the AP books. Scores on a math part of the SAT exam in a recent year were roughly normal with a mean of 515 and a standard deviation of 114. You choose an SRS of 100 students and average their SAT math scores. Suppose that you do this many, many times. Which of the following are the mean and standard deviation of the sampling distribution of X bar? If you look on page 4 of your reference sheet, it'll say the mu of X bar is mu, and the standard deviation of X bar is standard deviation over the square root of n. All I have to do is plug in the numbers. So the mean is going to be the mean, the same. So 515, I can eliminate C, I can eliminate D. Cannot be determined without knowing the 100 scores? No, that's a lie. We're going to do this many, many times, so technically we're not going to even have just 100 scores. We would have a lot of them. So we can do this problem, so you can cross off E. Does the standard deviation stay the same? No, it doesn't. N is 100, so B is our answer. A newborn baby has extremely low birth weight, ELBW, if it weighs less than 1,000 grams. A study of the health of such children in later years examined a random sample of 219 children. Their mean weight at birth was 810 grams. This sample mean is an unbiased estimator of the mean weight, mu, in the population of all ELBW babies. Which means that what? Well, remember, unbiased estimator would talk about the center of the distribution. If the center of the distribution of the sampling distribution is equal to the population, what's the population? Remember, population is mu. If I look at which one talks about my X bar equaling mu, it would be B. This, it says, is equal to 810. I can't guarantee all my possible samples will always get a mean of 810. That's very hard to happen. If it happened once, could it happen again? Yes. Would it happen every single time? I can't say that. No. B is the correct answer. It's the most correct answer when we're talking about an unbiased estimator. When will X bar equal mu? So B would be the correct answer for this one. The number of hours a light bulb burns before failing varies from bulb to bulb. The population distribution of burnout times is strongly skewed to the right. The central limit theorem says what? You better remember CLT, or some of you are going to be owing me some cupcakes. As we take more and more samples, what happens? CLT says that the larger our sample size, the more normal it becomes. So, which one talks about the shape of the distribution? That's what CLT refers to, shape. A is talking about their average burnout time gets closer to the mean. I don't care about the mean. I care about the shape. The average burnout time of a large number of bulbs has a same distribution with the same shape, which is strongly skewed. That is incorrect. It's not strongly skewed. It's going to be approximately normal. The average burnout time of a large number of bulbs has a sampling distribution with similar shape but not as extreme. That is not true either. CLT says it's going to be close to normal. So D will be the correct answer. Is anything ever exactly normal? Nope. So D is the correct answer.